Hi, this is Mal. Today we're going through another video on chapter 1 for IGCSE chemistry. And in this video we're going to talk about the heating curve. We're going to talk about Brownian motion and diffusion, as well as changes in state and kinetic theory. So let's get started then. Okay, let's start off with Brownian motion. So what is Brownian motion and what does it tell us about the motion of particles? So Brownian motion is defined as the random movement of particles in a liquid or a gas, and it is produced by large numbers of collisions with smaller, often invisible particles. So when we say invisible particles, we mean that they are just very small to see. And it is the observation of Brownian motion which proves the kinetic particle theory. So let's look at this diagram over here. So we can see we have a few larger particles here and some smaller, faster moving particles. So the large particles show a jerky and erratic movement. So what does this tell us about their movement? So it is kind of an erratic movement because of all the collisions with the smaller particles. So the smaller particles are bumping into the larger ones randomly and frequently, which gives them this erratic movement, and so that's exactly how we can explain Brownian motion with this diagram. Okay, let's talk about diffusion now. So this is the process in which different gases or different liquids mix together, and it's due to the random motion of their particles, because we know that liquids and gases have particles which move in a random motion. So diffusing particles are going to move from an area of high concentration to an area where there is a lower concentration, until the concentration of the particles eventually are all evenly spread out and occupy all of the available space in that container. So diffusion happens on its own and it doesn't require an energy input. And however, it does occur faster at higher temperatures, because we know at higher temperatures there's a higher kinetic energy, meaning that the particles are moving around faster, and therefore diffusion is able to occur faster as well. So let's look at this diagram over here. So we can see this is an experiment to show the diffusion of potassium manganate in some water. Now after a few hours, the concentration of the potassium manganate is going to be the same throughout the solution. So right now we have water everywhere, and we have the potassium manganate in just one part of the beaker. Okay, so what happens? So potassium manganate is purple, and it then begins to diffuse slowly. So the potassium manganate molecules diffuse throughout this solution from a region of high concentration, which is here just beneath A, to a region of low concentration, which is just above D. So we can see that the potassium manganate molecules are diffusing evenly, slowly throughout the liquid. So after 4 hours, we can see that it has been completely diffused throughout the entire beaker of water. We can see that because the particles are evenly mixed with the water at the top and at the bottom. So after 4 hours, an equilibrium has been reached. Okay. So let's talk about changes in state and kinetic theory. So when substances are heated, the particles are going to absorb thermal energy, which is then converted into kinetic energy. And the basis of kinetic theory is matter. This is the basis of the kinetic theory of matter. So heating a solid is going to cause its particles, because we know that solids have particles which just vibrate about a fixed position. They're not free to move. So when we heat the solid, these particles vibrate as the temperature increases, to the point where they vibrate so much that the solid now expands, and when the solid expands, the structure breaks down and it melts, forming a liquid. Okay, so with this further heating now, the liquid does the same thing and it then begins to expand more. Now, some particles on the surface of this liquid are going to be able to gain a sufficient amount of energy to overcome any intermolecular forces holding the molecules of the liquid together, and therefore it is going to evaporate. Now, what happens when the boiling point is reached? So when the boiling point is reached, the particles are going to gain enough energy to escape and the liquid boils. So we know when we talk about boiling, we mean that the temperature is even throughout the substance. Now, these changes can be shown in a graph, which is called a heating curve. And as the gas cools down, it would be the complete opposite of a heating curve, and this reverse effect would be called a cooling curve. And these curves show us how the changes in temperature affect changes of state. Okay, so here we have a heating and cooling curve. So we can see that if a solid is heated, kinetic energy increases and it then melts to form a liquid, and if more kinetic energy is added, it then vaporizes to form a gas. And the cooling curve is the same thing but in the reverse direction. So the gas would undergo condensation to become a liquid, because the kinetic energy is now decreasing in the opposite direction and the temperature is also dropping, therefore causing the liquid to freeze back into a solid. So during these state changes, we can see at these different points, there is no temperature change. So that's another important thing to remember. Alright, let's pay close attention to this exam tip. So while changing state, the temperature of the substance remains the same. So the heat energy is rapidly converted into kinetic energy. And this is what we call latent heat, and it corresponds to the horizontal sections of the cooling curve. So if we flip back to that, we can see we have horizontal sections of the cooling curve over here and over here. And this is what we mean when we talk about latent heat. Okay, so thank you, and that has been our video today. See you in the next videos.